Good morning to you. All right, so we are off and running. Fix the seat here. But we are off into 5.1. 5.1. We're supposed to be on 5.3 today. We're steadily falling behind. All right, so I'm going to talk twice as fast because we have no Monday, right? There's no class Monday. What are you guys going to do with yourselves without math class on Monday?
All the homework after the weekend.
I'll catch up homework. Independent math study. So I'll just teach twice as fast today to make up for Monday, okay? Ready? All right. So I think you've probably seen this before in your algebra days, right? Composition of functions. I'm jumping into number 8 because I think that'll actually be easier to start there. And if we got that down, go backwards. Excuse me. Okay, so composition of functions. So you know when they have the little circle thing like that in the middle? Remember what that means? You know how functions work. Like here's a f of x, for example. Let me go over here for a second. F of x is what? 4x plus 6. So you know what it means like if we put a 2 in the parentheses, for example, right? What does that mean? That means plug a 2 in where the x is. You know that quite easily. 8 plus 6, 14. So a function, I always use the toaster analogy. A function is like a toaster. You put stuff in, you get stuff out. Put in bread, get out toast. Put in frozen waffles, get out toasted waffles. So that's what a function is. Okay, and where's the plug-in for a function? It's always on the right of it. It's like that, isn't it? Right, the number to the right of the function plugs into the function. From right to left. That's how we've always done it, right? And that will continue. So my point is, this means G is plugging into F. Doesn't it? That's exactly what it means. It means F of G. If you want to write it out another way, you don't have to. It means that. It means G plugged into F. Just like functions always mean the right thing plugged into the left. All right. So that means I take the F function, which is right here, 4x plus 6, and what do I put in the x slot? Instead of putting like a 2 in the x slot, I put all of g into the x slot. So it becomes 4 times x squared plus 6. Instead of 4 times 2 or 4 times x, it's 4 times x squared because that is g plugged into f. So you know this, huh? And so there's our answer, 4x squared plus 6. At least that's part A. Good so far? Let's go do part B, huh? So part B says, okay, now go the other way. G of f, golf. G of f. So remember what function notation means. Who plugs into whom? The right side into the left. That's how functions always work, huh? So this really means G of f of x. It's putting one function into the other. So that means take the g function, which is the whatever you give me, I'm going to square it function, right? That's what g is, right? G of x equals x squared. So really that x, if you think about it, is like the holes in a toaster. It's the parentheses. It's the insert slot, right? That's what the x is in a function, huh? It says insert here, right? And so what are we inserting into g? All of f. So 4x, whoops, I missed the x. 4x plus 6. See how that's f inserted into g? Then we gotta do some algebra, huh? Gotta write 2 of those. And then FOIL that out. What's that? 16x squared plus 24x plus 24x plus 36. 16x squared plus 48x plus 36. There we go. There's golf. F plugged into G. Good. You've seen this before, huh? In your algebra days. So the function on the right plugs into the one on the left. Like always for function notation. Questions? All good? All is well? So then there's part C and part D. So part C says f of f. So f is going into f, huh? So it's f of x. So we're plugging that function into himself. Okay, so f of x is 4x plus 6. But remember, the x is like the holes in the toaster. It's the insert slot. That's what it really is, huh? And so it says, all right, whatever you put it in right there next to a 4 with a 6 added at the back. What are we putting in there? The whole 4x plus 6. Does that make sense? Then you can just do a little algebra. Distribute 16x plus 24 plus 6, 16x plus 30. And there's f of f. One more, let's just do it over here. G of g. Part D, g of g, which means g of g of x, right? G goes into g. So what is g of x? Well, g of x is whatever you give me, I'm going to square it. X squared. Remember, x is the insert slot, so it's x squared. So whatever you give me, I'm going to square it. What are you going to give me? X squared. So it's x squared squared, right? Which is, we're done. It's all well for those. So there's. Okay, let's try that one. So do part A there, f of g. F of g of x. So that's g into f. So this means all of G is plugging right there into F's input slot, huh? Like that? That good? Good so far. Now, we can't leave it that way because why? That's a fraction within a fraction. They call that a complex fraction. We can't leave complex fractions. So cannot leave. Math Excel won't take it that way. Cannot leave a complex fraction, which means fraction within a fraction. So we cannot leave a fraction within a fraction. So we have to do something about that. So how do you clean up? Do you remember, anybody remember from your algebra days? These are covered in algebra usually. Complex fractions. How to clean them up, make them a normal fraction. Yeah. And where do we multiply that x? To everything. There, there, and there. Yeah. Yeah, now where to come up with x? Because that's the one causing the problem, right? If he wasn't there, it would just be a normal fraction, huh? It's his presence that is making the thing be a fraction within a fraction, right? A fraction in the denominator. So he's the problem child, right? He's the problem, right? So then you multiply everybody by him. Notice I'm doing the same thing to the top and the bottom of the overall fraction, so I'm not changing anything, huh? Right? I always call it plastic surgery. I'm removing the wrinkles, but it's the same person. It's going to look different, but it's the same fraction in the end, right? I'm not changing anything. I'm just making it look different. So what do we get then? 2x, these cancel. That was the whole reason we did it. 9 minus 9x. There we go. Does that make sense? A little cleanup on that fraction. So whenever you got fractions within fractions, just multiply top and bottom by the LCD, basically. Tim?
So I did that whole thing, I got the same answer, but I multiplied the x to just a singular 9, and then it was like 2 over 9 minus 9x over x, and then just multiplied it, the reciprocal, I guess, or... I don't know,
yeah.
I still got the same answer, but...
Right. You just did common denominator over there. Yeah, you can do those kind of ways. I think this is easier.
Kind of like what we did.
What did we do? Oh, yeah. Yeah, so you went over here and said, okay, look, I'm going to make these guys, put this over 1, top and bottom by x, so then it's 2 over 9 over x minus 9x, but they're both over x now, and then flipped it up. Right? Yeah, that'd be the same result, I think, because that x would go to the top, yeah. I think, that'll work too. So, either way. on
And
that.
that second process would work for other problems as well.
All these kind, yeah.
Okay.
Good on that one? All right, so the rest are going to be the same, g of f and f of f and all that. So I'm just going to, okay, yeah. Let's go back here. Now let's answer the domain. Yeah, that's an important question. All right, so here, let me get a fresh screen here. Okay, yeah, I forgot about the domain stuff, so let's do that. All right, so back to the answer. F of g, again, was 2 over 9 over x minus 9 at first, right? And that's important because it first matters. I'll explain in a second. Let me go through the process again real quick. Then I multiplied top and bottom by x, and I got 2x over 9 minus 9x because those cancel, right? And that was my final answer. Okay, now, here's the question. What's the domain of that? This is the f of g right there. What's the domain? Remember how we do domain? Remember what we always do? We say denominators, you can't be 0, and inside, if you have a root, if you have a root with something inside, the inside can't be negative, must be greater than or equal to 0. We just look for those two problem areas, right? Like you can't put knives in the toaster, you can't put zeros in a denominator or negatives in a root. And that's how we handle domain, right? So what do we have here? We have a denominator. And so we say, okay, denominator, you cannot be 0, which is true. There's an extra special wrinkle coming here, though. Move that over, divide by 9, x not equals, x cannot be 1. And that makes sense, because if x is 1, that's going to be 9 minus 9, or 0 in the denominator. That's not allowed. So x cannot be 1. It can be anything else other than 1. Or 0, it turns out. Why, Robert? Why is 0 a problem?
Because the g of x has an x in the denominator, and if it was 0, we can't find it, we can't plug it into the f of x.
Exactly. Yeah, so here's the story. Here's the extra wrinkle in the story. Basically, you know, when you were in algebra, they kept life simple. And they said, hey, there it is, just do that. We just cleaned it up, and there it is. Really, though, when you clean something up, it's not really exactly the same as the original. Here's how it's not. This is the original. Let me go back. What was the original before I did any of this cleanup? Before I put these x's here. Let me go back here. This was the original. Right here, right? What? Remember, same issue. Any denominator can't be 0. Well, that's a denominator right there. So x also can't be 0. So you have to give any restrictions on the original denominator and the final cleaned up version. That's the story. Does that make sense? When you plug one function into another and have this cleanup thing, you have to make sure that there's no problems caused by the original denominator also. That's the original denominator, isn't it? Does that make sense? That's an original denominator. So notice you can't really put 0 in there. Now, why didn't we see that over here? Well, because when we did our little x multiply thing, it vanished. So it hid the problem from us in the cleaned up version. But it's really there. Does that make sense? So, let me write a note. When a domain for an f of g kind of thing, you must check original denom before algebra cleanup. So you must check it before. Yeah.
Why don't you just solve for the domain on the original in general?
Yeah, you could. Yeah, let me show you. Exactly. That's the other thing. I don't know. I never know how many details to give you and confuse you. But you're totally right. So there it is, 2 over, what was...
It seemed like it was becoming overcomplicated.
Yeah, if that is easier thought for you, then that's right. 2 over 9 over x, 2 over 9 over x. Yeah, what you could do, here's another. Here it is before the cleanup, right? Now, of course, we have to clean it up to give the final answer. But as far as the domain issue, here's another way to say what I'm saying. As far as the domain issue, what again is the domain? Let's say it out loud. At least I'll say it out loud. It means any denominator can't be 0. Well, if you think about it, we have two denominators. We have this, and the whole thing's a denominator. That's the other way you could do it. You could just say, okay, look, x itself can't be 0 because he himself is a little bitty denominator, and the whole 9 over x minus 9 can't be 0 because that whole thing's in there. There's really two denominators, aren't there?
You just take the g of x and set it equal to 0.
And if you just solve this, let me hold on. If you just solve this and move this over, how do you solve this? Move this over, and then what? How do you solve that? Put this over 1, cross multiply is probably about the easiest thing. So 9 times 1 is 9 times x. 9 equals 9x divided by 9. This is supposed to say not equals all the way here. Not equals. And that's what? There's our not equals 1, which is what I got from the second part after the cleanup. So if you want, you could just never mess with the cleanup. You see what I'm saying? And just set the two versions of the denominator not equal to 0. Am I confusing you by giving those extra details? So there's two ways to do it. You can either take the original little denominator and the cleanup, or just take both the originals, the little and the whole denominator. You'll get the same two answers. Neither of those is allowed. So either way. Robert, what did you say?
I was just saying, if you know what you're plugging into it, you can look at the original on the top, the original g of x, and just
Yeah.
say x cannot be 0 right there.
Yeah, good point. Good point.
And when you have your f of g, your composite.
Just do the cleanup. Yeah, that'll work. That's a good idea. That'll work too. A lot of ways to go. When I was first a brand new teacher, I used to teach that way. In fact, pre-calculus was the first thing I ever taught. And I thought, oh, I'll be helpful. I'll give them like 3 ways to do everything. That totally confused everybody. So I learned after that students prefer one way, done 10 times in a row. But anyway, so that's why I hesitate about other methods. But you guys are right.
How would you write that in the domain? Like negative?
Oh, yeah, so they just want you to say x cannot be, 0 and 1. I think, I don't know if they want interval notation or they have the not equals thing.
If it was interval, how would it be written?
Yeah, so interval be negative infinity up to 0, 0 to 1, 1 to infinity. See how I just skipped 0 and 1? Went all the way basically from negative infinity to positive infinity, but just skip 0 and 1. If they want interval or if they want it like that. All right, good. Okay, yeah, so that's always an issue you got to watch out for. So original domain, that. Yeah. All right, so let's try that one, f of g. So that means we're going to take all of g and plug it in there and there. Do you see the mess we're talking about, guys and gals? Into those 2 slots. The whole g plugged into both those. And this is parts A, B, C, and D. This is a terrible problem. See what I'm saying? That makes sense there? I got that. Now you got to clean that up. Well, right away, hey, can we right away see a domain problem right now before any further cleanup? What little domain problem will there be? Yeah, x cannot be 3. Let's just make note of it. That's kind of like what Robert was saying. You could have just looked at g right away and said x can't be 3. That's right here, x cannot be 3, because that'll make that tiny domain 0. We've handled that. Now just go on and clean the thing up, and after it's all cleaned up, then you can set whatever the cleaned up denominator is not equal to 0 also, right? Now, how are you going to clean that up? Remember, you identify the denominator, which is him and him, so it's the same thing, and you give it to everybody, top and bottom. So x minus 3, x minus 3, x minus 3, x minus 3. Does that make sense? Everybody gets one? And these cancel. So what does that leave us? X plus 2 minus 7. In fact, I'm just going to distribute this one right away. Minus 7x plus 21 over x plus 2. Distribute this one. 6x minus 18. What's that? X minus 7x. What's that? Minus 6x plus 23. X is 7x minus 16. There we go. And for the domain issue, we already have x can't be 3 because of the original before the cleanup. And then we would also say 7x minus 16 cannot be 0. So x cannot be 16/7 also. Is that okay if I just skip through that like that? Am I going too quick? I know algebras, I want to slow down there, but I don't. Both. I want to and I don't. But I do. I know algebra is really where I want to be helpful to you because that's important. Is that okay? Questions I can answer on those algebra steps? So like definitely this one, what is number 11, is going to be a ton of work because it's A, B, C, D, and all four, you know. That's the thing. You know, you want to go on to calculus. Make yourself do all four of those parts until you can really do them flawlessly. Is that good? I just multiplied through by the denominator and then canceled, gathered like terms. The minus sign here has to distribute, you know, those easy to mistake all those little things there. That good? Okay there? All right, so. Okay, so see how I have S. Here's where it'll become useful to you to start to look kind of close at the letter that's in the parentheses. You might not have needed to pay much attention to it up to this point in your math career. Let me write those out. So look closely at what they're saying there. So now it's important to think about. But remember, we've got to deal with it a little bit. The letter in the parentheses, that's the independent variable, we call that, right? So the R is the independent, meaning he's independent. I don't know how else to say it. Meaning that he doesn't depend on anything, right? He can be whatever he wants to be, right? Plug in a 2, plug in a 3, plug in a 7. And S is the dependent variable. In other words, he will respond, right? If R is 1, then S is going to be 4 pi times 1 squared. S is going to be 4 pi. See how S responded to R's choice? R said, I'm 1, and then S said, okay, then I'm 4 pi. See how we mean independent, dependent, right? So S is the dependent variable, at least in this first equation. So R is whatever he wants. S responds. S is a function of R. This is another way it's said. S is dependent upon R. It's a function of R, right? Like your grade is a function of how much homework you do, right? How much homework you do, your grade will respond. That's the same kind of thing, right? So that's what we're talking about here. Now, look in the second one. R, radius of the balloon, is a function of time. It's dependent upon time. Now, the radius changes over time because the thing's filling up or whatever, right? So as time goes by, the radius grows. I assuming I read it quick. Are they filling up a balloon? Yeah, right. The radius is increasing with time. They're blowing up a big balloon. Hot air balloon or something. So over time, as time goes on, the radius gets bigger and bigger and bigger. And as the radius gets bigger, the surface area, of course, is growing. So, well, now okay, great, you got all that. So what do they want? They want this. Now what does that say? S of t, notice. Not just S of R. S as a function. Now you know what that means. They want blah, 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 blah with t only. Numbers and t. Just t as the only letter, huh? So how do I make a function where t is the only letter? Well, this is what R is, and I plug it in for R. It's it's a plug one function into the other thing. So it's 4 pi times R squared, and what's R? 5, 6 t squared. Square that, and you see we'll have S as a function of t only. See what we're doing there? Because R is 5, 6 t squared, I plug that in for R. So what do we got? 4 pi times, what's that, 25, 36 t to the fourth when you square everybody in those parentheses. And then the 4 is over 1, so it multiplies the 25 in the top. Or actually, you know what? I should cancel it with the 36, huh? That's what I should do. 4 goes into 36 9 times, huh? So we get 25 ninths pi t to the fourth. And there it is. We found S as a function of t only. That's the only letter. Pi's not really a letter. It's 3.14, right? Approximately. So we did it. We've got surface area as a function of time. We can plug in any time, and it'll tell us how much surface area is currently there in that balloon, because that balloon's blowing up. Good on that? Makes sense? Questions I can answer? So just a fancy plug one function into the other. Let me show you what they're doing here. All right, so see how they have this cost function, and they have this other function. And basically, n is this. Plug that in there for n, huh? So just plug in one function into the other. So the C will be 20,000 plus, what is that, 6,000 in, but instead of in, I'm going to put what in is. In is 700t minus 15t squared. That's what n is. And I'll get c. What do they want? C of t. C is a function of t. Yeah, that's what I'll have. I'll have only t as my variable. Distribute. What's that? 42 with 1, 2, 3, 4, 5 zeros, huh? You can just count the zeros. 6 times 7 is, I just multiply the number. 6 times 7 is 42, and then count all the zeros. 5 zeros, whatever that number is. 4,200,000 t plus, no, that's minus. It's just a scribbly minus. Minus. 6 times 15 is 90, and then 3 zeros. T squared. There we go. So it's just plugging one function into the other. Good? Easy pickings there. So they got volume, it's pi r squared h. And then see how it says height is 5 times radius? H is 5r, isn't it? So grab that, plug it in for h. What's h? 5r. So multiply that together. Pi times 5. You can put those in any order. Probably you put the 5 in the front. It's more normal. But that's fine right there. So we got volume as a function of radius. Radius is the only letter. Good with all those? Okay. All right. So I'm going to go back now to the first. Well, I don't know how messy it is. Maybe it's worth our time, at least to do one direction of it. So f of g. So they want us to do f of g, which means g into f. So that means plug all of g here into x's input slot. And I'm trying to make it nice so it's readable. Does that make sense? So I'm trying to do color coding to help. See, F is C times whatever plus D. That's what F says. C times whatever plus D, right? And then I'm putting G, right here, this is G, into F. Am I good? Then we got to clean that up with some algebra. How does that work? Well, right away, C multiplies this. Oh, you know what you might think? Yeah, let me help with that. You might think that I've just seen it, and this is important. Here comes another weed in the garden of a typical algebra student that was in my garden too, and you got to pull this weed out to have a happy life in calculus. You might think it goes all the way across. It does not. It's an important algebra lesson to learn. Why? Because this is times here. Distribution never crosses a times barrier, right? What is distribution? Distribution crosses two things added or subtracted, doesn't it? That's what it only crosses one times barrier. How about put that way? Not two. In other words, you would never go, I'm going to multiply 2 times 3 times 4. Think about that for a minute. You would never go boom, boom. That'd be crazy. That'd be 6 times 8 now. 48. It was never 48. It was 2 times 12. It was 24. See how wrong that would be? Am I going too quick? I want to show you with numbers what's clearly not true so that we don't do it with letters. Does that make sense? And so an easy way to stick it in your mind is distribution only multiplies once, right? You can only multiply once. If I did this is so wrong because it's times here and then times again. We never double times. Distribution is when you have adding or subtracting. Right? It crosses a times barrier once only. And then several adding and subtracting are fine. Right? So, with that in mind, this C will not go to all three of those. It will only go to this first one. Right? Because this is the times barrier. It can't cross this other times barrier also. Because that's really something multiplied by something. This is like 2 times 3 times 4, you see. It can't go there and there. See that? Rana?
I thought you had to work from the innermost of the.
Oh, you don't have to. You know that. Let me show you. Right? If you have this, you could do the inside first, but you know you could also get 6 plus 8. That's what distribution is an option, so you don't have to do the inside first if you don't want to. Remember that? Makes sense? These algebra rules come in more. See how like you know algebra, but you need to know it deeper. See what I mean? That's really it. It's like you've heard some of the things, but it's got to be deeper, deeper, deeper. Really, they could call this, and you know when you'll know algebra? When you finish calculus. Then you can say, I know algebra. That's when you'll really know algebra. Right? So that's a good question. That's all the kind of stuff I want to help with. That's the whole point of distribution, that you don't have to do the inside first. Now, why would we want that? Well, because sometimes there's an x there, and you can't do the inside first. Make sense? That's what distribution is. Yeah, so, all right. So, because I know you're thinking of the PEMDAS rule, right? Please excuse me, dear Aunt Sally, parentheses must be first. Well, that's exactly what distribution is an alternative to PEMDAS, a legal alternative to PEMDAS. All right, this is what you want to do, is stay up late at night while you're doing your homework, thinking more deeply about these algebra rules and letting them sink deeper. That's exactly what you need to do. All right, so anyway, I've talked about this one a lot. So c times 1 over c, these guys are just going to cancel, and it's just x minus d plus x. See what happened? Those canceled, huh? X minus, you can keep parentheses if you want to. It's doing nothing. So that's just x. That's just a fancy problem to end up x. All right. Hey, what does that mean? Anybody know what that means? Or you have another question? Go ahead.
I was wondering, can I distribute the 1 over c into x minus d first and then distribute the c?
You could. You totally could. Good question. That's okay too. It's not easier, but it's okay. Yeah, you could leave this c out here. I hear what you're saying. And then just let this guy distribute. First you get x over c minus d over c. Like that, right? That's what you're meaning, right? Yeah, and then distribute this guy, and he'll cancel, and see how we'll get the same thing in the end? Yeah, that's okay too. It's easier, though, just to go boom, boom. It's gone right in the beginning, if you know all those rules well, and you don't break a law. The math cops will come for you. All right. So what does it mean? Think about what just happened. We've been lost in all the algebra for a minute. Let's step back from all the algebra and think about what just happened. I took an x, and I took an x and I put it into G, and then I put it in, and I took the result and put it into F, and I got back x again. I took an x, and I ran it through both machines, and it came out the way it started. Are you tracking with me, right? Because well, where'd you do that? Right here. F of g of x. F of g, I didn't show the x, but I mean, that is g of x right here, right? I did f of g of x, and the result was x. So what does that mean? That means I took x, right? It's a toaster. And you put something into one machine, out popped the whatever, put it into the other machine, and it came back the way it started. It came back x again, the way it started. What does that mean? If you take something, put it in one machine, it does something to it. Take that output, put it in the next machine, and it changes it back to the way it originally started. What do you know about those two machines? They're what?
Well, they have, I think I know kind of where you're going.
They're inverses.
Yeah, they have inverses.
They're opposites. They're doing the opposite thing. Whatever the first machine did, the second machine undid it and made it back the way it started. Right? And that's exactly the test for inverse functions. Whenever you do f of g of x and it comes out to just be x, you go f and g are inverse functions. And that's what they're proving on this problem, that this function is actually the opposite of that function. See how they are the opposites? F is the multiply by c add d function. G is the divide by c subtract d function. They're opposite functions. They undo each other. And they, right? If I said I took a piece of bread, put it in the toaster, out came toast, then put it in my de-toaster, right? If there was such a thing. Turned it back into bread. That'd have to be that if it came back bread after the second machine, that would have to be the opposite of the first machine. They're inverses. That's the point of that question. All right. So that's what they're going to ask right here. Are these equal? And the answer is yes. They're both just going to be x. You'll see. Conceptual. Not hard. It's pretty quick if you get the concept. So, okay, they're asking f of g of 2. So what does that mean they want me to do? They want me to take the 2 and put it into g. and then whatever, put the bread into the toaster, and whatever comes out, pop, and then put that into F, and tell me what comes finally out the door, right? It's like putting your toaster in your refrigerator, right? One machine inside of another. You could do that. You could put, I don't know where the power cord would run, but you put your toaster in, and then you could think what that would do, right? I'm not just being silly. I'm trying to make it solid in your mind what it is we're doing. So I took a piece of bread, and I put it in my toaster that's in my refrigerator. Push down the lever, close the refrigerator door. A few minutes later, that toaster would toast that bread, pop, it would come up, and then the outer machine would start, right? It went through the inner machine, right? The toaster's done with it, made it toast, right? And then the refrigerator would start doing what it does to anything you put in it, chilling it, right? And so after a few minutes, I could open the refrigerator door, and I'd have my chilled toast. I don't know why anybody would want that. But that's the idea of what we're doing, right? We're putting something in one function, it comes out, goes into the second function, finally out the door, right? We're running stuff through two machines. So that's the idea of this table and the graphs we're going to do next. If I put a 2 into G, now what does this table mean? Let's make sure this is making sense. What it means, see, here's the x values, and here's the f of x. So for example, if you put -3 into f, what's coming out? -9. Let's make sure you understand what the table's even saying first off. Do you get how you do the row and the column, and whatever they line up and wherever they line up and meet, that's what comes out of the toaster, right? So if you put -3 into F, you're going to get out -9. If you put -3 into G, you're going to get out 3. That's what the table's telling you. If you put a 1 into F, you're going to get out a -1. Right? If you put a 3 into G, you're going to get out a -3. The table making sense? Tells you these are all the outputs. All of these are outputs. Right? And the X's are the inputs, aren't they? So up here, so these are all outputs. Whoops. These are all outputs. And this top row is the inputs, right? It's what you put in. Okay, so with that in mind, what are we doing? We're putting 2 into G. Okay, so they want me to find G of F of -1. So that means -1 into F, find what pops out and put that into G, right? All right, so now how do you do that with a graph? Well, remember, inputs are X's, Y are outputs on the graph. Right? The vertical Y, these are outputs. The horizontal X, these are inputs. That's the role of X and Y on a graph, right? X is inputs, Y is outputs. Okay, so what does that mean? So let's start with putting a -1 into the F machine. So look on the F graph. Look on the F graph and decide where, when you put in -1, here's -1. You get out right there. You get out a 2. 2 pops out. Wait, did I do that right? Yeah. So because I'm looking at the F graph here. Here's the F graph, right? It's the bottom one. Looking at the F graph, when you put -1 X value in, go up to the graph, you get a height, a Y value 2, because that's the point back 1 up 2. The X value -1 leads to the Y value 2 on the F graph. Put in -1, get out 2. That's a dot. Every dot on a graph is an input-output relationship, isn't it? It's an XY, input-output. Put in a -1, get out a 2, says the F graph. So we put in a -1, pop, out comes a 2. Now we put the 2 into G. What's going to happen with that? Where's the 2 in the G? So look for X value of 2. Here's X value 2. There, that point right there, huh? What is that point? Over 2, 2. Yeah, so XY. Put in a 2 into the G graph. Also get out a 2. Answer's 2 to part A. See how we track that through? X, Y, inputs, outputs for any function. That's how graphs relate. All right. All right, so F of G of 4. What do they want me to do for F of G of 4? Well, they want me to take the 4, and now they're doing numbers instead of an x. Do you notice that? We did problems 8 to the end. We started with 8 to the end because those were the ones with just x's. I thought that's what you'd be most familiar with and used to. But now I'm backing up. See the difference? It's if they just said, give me f of g of x, I would say, all right, just, all of g, pop it into, whoops, I missed. Pop it into f right there. It would just be 3 times 4x squared plus 9, and then distribute 12x squared plus 27, right? That would be f of g of x, right? But they're not asking me f of g of x. They do that on problems 8 to the end. They're asking me f of g of a number, 4. So I'm going to take the 4 and put it into g. So let's take the g function, which is 4x squared plus 9, g of x, and put in a 4. Get 4 times 4 squared plus 9. What's that? 64 plus 9, 73? So you put a 4 into g, you get out of 70. So pop, out comes the 73 from the toaster going into the refrigerator now. Now it's going into f. The 73 is going into f. So what's f of x? Well, it's 3 times x. So plug a 73 into f. 3 times 73, 210 and 9, 219? 219. There it is. Does that make sense how we did numbers instead of just letters? By the way, you know what you could do? I probably did this too quick. Here, let me do this slower. You could just do the f of g of x thing, and when you're all done, just plug the number in. That's an option. It's not really easier. It's about the same probably. So what was f of g of x again? They didn't really ask me that, but I could have just said, look, I'm just going to find f of g of x, and then just plug the number into that. That would work. So that would be what? Was it again? So f of x, so it's g into f. So all of g plugging into f here. So that would be 3 times all of g, which was 4x squared plus 9. This is an alternative. Distribute 12x squared plus 27. So that's f of g of x. Now you can say, okay, I'll just use that to find f of g of 4. Because that is the function, f of g of anything. So now plug in 4. 12 times 4 squared plus 27. That's 12 times 16 plus 27. I'm betting that's 219. Somebody have a calculator? See how it comes out the same. So either way on that one. Does that make sense? So we covered that section, and we're drastically behind at this point. Okay. 5.1 then. 5.1 is due on Tuesday.